At the end of lecture 21, we touched on the effects of X-ray absorption. We saw that when the X-ray beam has to pass through matter, it is absorbed, and that absorption can reduce the intensity of a diffraction peak. This is a relatively short lecture where we're going to look at that in a little bit more detail and think about some of the practical consequences of X-ray absorption. So if we think about the absorption of X-rays as it passes through matter, we can quantitatively express that with this equation. And this equation should look pretty familiar for anyone who's done, let's say, a Beer's law plot of UV or visible light passing through a solution. Right? The percent of X-rays that are transmitted, that is the intensity of the X-ray beam divided by the initial intensity, is equal to e to the minus mu x, where mu is a parameter that we call the linear absorption coefficient. It has units of 1 over distance, and x is the path length. The product of mu x is dimensionless. Now we can calculate the linear absorption coefficient mu using the equation here at the bottom. And in this equation we have the density of the material, and that's multiplied by the mass fraction of each element in the material times its mass absorption coefficient. It's also the symbol mu here with the prime, but this is a mass absorption coefficient. This has different units than the linear absorption coefficient mu. So let's illustrate how we might calculate the linear absorption coefficient for a material. We're going to do corundum, alpha aluminum oxide. So to do this calculation, we're going to need to know the density. The density of aluminum oxide, we can look that up, or we could calculate it from its crystal structure. It's 4 grams per centimeter cubed. We'll need to know the molar mass, so we can calculate the mass fraction of the different components. The molar mass here is 2 times the molar mass of aluminum plus 3 times the molar mass of oxygen. That gives us 102 grams per mole. And then we can look up the mass absorption coefficients for aluminum and oxygen from this NIST website. And I'm going to tell you that these mass absorption coefficients depend on the wavelength. Here we're going to do the calculation at a wavelength of 1.54 angstroms. Right? That's the kind of radiation that we get from a copper X-ray source. And when you go to this NIST site, it's not going to ask you for the wavelength, it's going to ask you for the energy of the photons in kiloelectron volts. So 1.54 angstroms is 8 kiloelectron volts to 2 significant figures. And we see that aluminum is more absorbing than oxygen, and that's what we expect because aluminum is a heavier element than oxygen. So now we can take those values, come back to our equation, and plug them into the equation. We've got the density, 4 grams per centimeter cubed, and then this term right here, that gives us the mass fraction of aluminum in this material. We're going to multiply that by the mass absorption coefficient of aluminum for X-rays of this wavelength. Here's the mass fraction of oxygen times the mass absorption coefficient of oxygen. And when you plug all that in, you come up with a value of 129 inverse centimeters. So these linear absorption coefficients, the units are going to be 1 over distance. They're normally expressed in 1 over centimeters. Now, I did the calculation here for illustrative purposes, but if you go to this NIST website and you put in the density of your material, it'll actually do the calculation for you. We can plot the propagation of copper K alpha X-rays through aluminum oxide on a plot like this. And what we see is that, here initially, before the X-rays enter the aluminum oxide, the intensity is I naught. But by the time we get a 0.5 millimeter into the aluminum oxide, they've practically all been absorbed. So the amount that are not absorbed is so low we can't really even see it on this plot. So that's something to keep in mind if you want to do a diffraction experiment. If you were going to analyze a single crystal of aluminum oxide and you were using copper K-alpha radiation, you would want your crystal to be considerably smaller than half a millimeter. So you'd want a crystal that might be 100 microns, 0.1 millimeter. And in general, a lot of single crystal diffraction experiments are done with crystals on the order of a few tenths of a millimeter to minimize the absorption effects. It also has implications when we want to do powder diffraction in a transmission mode, as we'll see in a few slides. Now, if we were to change the wavelength, then the absorption of X-rays by the aluminum oxide would change pretty significantly. So if instead of using a copper X-ray source, we were to use a molybdenum X-ray source, and this is pretty common, and in fact, it's the most common source you see for single crystal instruments, then all of a sudden the absorption goes down quite a bit. So even after the X-rays have traveled through 1 millimeter of aluminum oxide, they're still only about 70% attenuated. If you were to go to a synchrotron source where the wavelength of the incident radiation can be varied, usually by using monochrometers on the incident beam, you might have a wavelength like 0.4 angstroms. This is a pretty typical wavelength for the powder diffraction instrument at the advanced photon source. And now you can see that after passing through 1 millimeter of the sample, that you still have about 75% of the X-rays that have not been absorbed. You could obviously work with larger samples when you have these shorter wavelengths. Now, what about if we were to go to a somewhat heavier material? I mean, aluminum and oxygen are both pretty light elements, at least for an inorganic chemist. What about if we were to go up just a little bit to a first-row transition metal like manganese oxide? Well, now I'm showing the attenuation at these three different wavelengths for manganese oxide. You can see if you look at our linear absorption coefficients, they've gone up by about a factor of 10, and consequently, we're seeing a lot more attenuation here. With copper K-alpha radiation, the X-rays are almost entirely absorbed before you even get through 0.1 millimeter of your sample. When you go up to, say, 0.7 angstroms, molybdenum radiation, you do get more penetration, but still by the time you get to half a millimeter, the X-rays are almost totally absorbed. And then if we were to go to a synchrotron, of course, once again, we see a deeper penetration depth, but here we're seeing more substantial absorption than we did see with the aluminum oxide. And that's what you expect because manganese has more electrons, and the heavier the element, the more absorbing of X-rays it's going to be. Well, what is the practicality of all this? So, we can calculate this, but what are we going to do with it? How much absorption is too much absorption? I'm going to leave the discussion of this for single crystal measurements until later in the semester, but we can talk about powder measurements that are in transmission mode. And the way that's normally done is to pack your sample into a cylindrical capillary, and this is the common mode at which powder diffraction measurements are made, for example, at synchrotron sources. And although we're not talking about neutron diffraction here yet, this is almost exclusively the way measurements are made at neutron sources in a transmission mode. You can apply the same sorts of ideas to those measurements. But if we're talking about X-ray diffraction, we want to calculate this parameter mu r. So mu is our linear absorption coefficient, and r would be the radius of our cylindrical sample, the radius of our capillary. Now, we could just use the standard mu that we've been talking about in these calculations and just multiply by the radius of the capillary. We would be all done if the sample was perfectly packed into the capillary so that the density of the sample in the capillary is the same as the density of a single crystal. But in practice, when you have a powdered sample, the packing density or the packing fraction is not 100%. It doesn't have the same density as a single crystal. So we have to account for that by saying, all right, our powder is only going to be 60% of its theoretical density. So once we take that into account, multiplied by the linear absorption coefficient that we just talked about, multiplied by the radius of the capillary, we get this mu r term. And then that term should be ideally less than 1. Okay, if mu r is less than 1, then the absorption isn't going to be a big problem. And probably you can analyze your data without making an absorption correction. There's certainly no harm in doing that, and that would probably give you a little bit more accurate displacement or thermal parameters, but you don't have to worry too much about it. On the other hand, if mu r is larger than 5, the transmission is going to be highly problematic, because at those levels, actually the X-ray beams, most of them can't make it all the way through the capillary. So you end up getting diffraction from only a portion of the volume of your sample, largely the skin around the outside of the capillary. And there's really no good way to correct for that. So we want to avoid making any transmission measurements when mu r is larger than 5. Well, let's go back to the two kinds of materials we've talked about today, aluminum oxide and manganese oxide, and see if we could use this approach to decide, well, how big could our capillary be and still we would be okay to do a transmission measurement. So if we look at the aluminum oxide at copper K alpha wavelength of 1.54 angstroms, we can see that if we assume the packing of the aluminum oxide in our capillary is about 60% efficient, then we'll be just fine as long as the radius of the capillary is less than 0.13 millimeters. Well, that's pretty narrow. That's a diameter of 0.26 millimeters. But I will say in my past experience at filling capillaries, we generally went at the smallest end for 0.2 millimeter capillaries and at the largest end for 1 millimeter capillaries. At 0.2 millimeters, it's not very easy to fill them, but it is possible to do that. We see that we could tolerate a bigger capillary, one that would have a radius up to about 0.64 millimeters. So that means the diameter of that capillary would be over a millimeter. Those are quite easy to fill. So you could do transmission measurement through a capillary of aluminum oxide with a copper K alpha X-ray source. If you go to a molybdenum X-ray source, you can see that we can use even larger capillaries. Now, generally, we're not going to use a capillary that's 1.4 centimeters. That will degrade your resolution significantly. But the point being that here we don't really have to worry about absorption effects. If we were to look at the manganese oxide for the 1.54 angstrom wavelength, we've got some problems here. We don't want the diameter of our capillary to be any bigger than 0.14 millimeters. Well, that's a very narrow capillary, and I would say good luck filling that. But if we go to a synchrotron, where we can take the wavelength all the way down to 0.4 angstroms, then you can see, okay, now no problem, right? We're good with any capillary that has a diameter less than 2 times 0.56. So any capillary that is less than 1 millimeter in diameter is going to be just fine. These are the kinds of considerations you want to take into account when you're planning a diffraction experiment, especially one where you're going to be doing a transmission measurement. Now, one useful source that I found on the web in preparing this lecture is one from the Advanced Photon source, the powder diffraction beamline there, 11BM. They have an absorption calculator. You can find it at this URL. And what you do is you type in the empirical formula of the compound that you want to look at, and you tell it what is the radius of your capillary and what is the packing fraction of the sample in the capillary. So if I do manganese oxide, and I assume that I'm going to get about a 60% packing fraction, and here, just to see how it would work, I chose a capillary radius of 0.25 millimeter. So that would be a diameter of 0.5 millimeter. That's a kind of capillary that you can fill. And then we get this plot. And so what are we seeing on the plot? Well, the x-axis is the wavelength of the X-rays. In this package, it'll ask you to pick a wavelength, and here I picked 0.71 angstroms, and so you can see it's telling you, okay, here is the wavelength of your planned experiment. But you can see from the graph what it would look like if the wavelength were 1.5 or 0.4 or anything else. It also shows you a red line, that's mu r equal to 5. We don't want to be above the red line. And a blue line, mu r equal to 1. We'd like to be at or below that line if we can. And then you can see the absorption of oxygen in green, manganese in blue, and the overall compound in red. And you can see from this that most of the absorption is coming from manganese, only a very small amount from oxygen. Now, at the wavelength that I envisioned for this experiment of 0.7 angstroms, I can see that my mu r is right here. I don't know, something like 2, 2.5. Well, that's okay. I can probably live with that as long as I make an absorption correction when I'm analyzing my data. And by the way, the input for the absorption correction is the value of mu r. If I were to do this experiment with a copper X-ray source, you can see then I'd be out here. My mu r would be over 15. And so then I would need to use a capillary that's at least 3 or 4 times smaller, and that's going to be hard to do. So it's not really a feasible experiment on a copper X-ray source. If I were to go to a synchrotron and do it at 0.4 or 0.3 angstroms down here, you could see then I would be good. So this program, it can be a really helpful way for you to plan your experiments. Before we leave X-ray absorption, I want to say a little bit about absorption edges. Notice how this curve, the absorption, is going up strongly, and then all of a sudden it drops. And if we had a wide enough range here, we could see then it would start to go up again. This precipitous drop occurs at an energy where the manganese atoms have an absorption edge. And being around the absorption edge, as you can see from this plot, things change pretty dramatically. We can see that we wouldn't want to do this experiment on manganese oxide using 1.5 angstrom X-rays. But what about if we were to switch from manganese oxide to nickel oxide? Now nickel, as you probably know, is a little bit heavier than manganese, so you would expect that it'll be more absorbing. But notice that now for nickel, the absorption edge has moved to higher energies, that is, moved to shorter wavelengths, and now 1.54 angstroms is just on the other side, on the long wavelength side of the absorption edge. And so on the long wavelength side of the absorption edge, just past it, the absorption drops dramatically. This is actually a really good place to work when you're doing X-ray diffraction experiments, just beyond the absorption edge. Now, the other thing that's happening around an absorption edge, which doesn't really captured in this plot, is that the elements actually start to scatter as though they have fewer electrons than you would expect them to have. And that effect is a maximum right at the absorption edge. And so we can use this, it's called resonant scattering. It's going to come into play somewhat when we talk about single crystal methods of trying to assess things like if you have a centrosymmetric space group or if you have a chiral space group. It can be used for, let's say, trying to accentuate the difference in scattering power of two elements that are close together on the periodic table. And at any rate, it is something that you have to think about when you're doing refinements. When you get close to an absorption edge, the scattering power of your element actually goes down. The other thing that's not quite captured on here, but once you go past the absorption edge, let's say we were to collecting right here, well, not only does the sample become pretty highly absorbing, but it also starts to fluoresce a lot. And that fluorescence will give you a larger background. So you really don't want to be collecting data at wavelengths that are just shorter than the absorption edge. And that happens with copper K alpha radiation when you collect data on cobalt and iron. And so those samples can be difficult to analyze with the diffractometer based on copper radiation. There are other elements, like some of the rare earth ions, that also are somewhat problematic with copper radiation. Let me finish with just one more point, and that is coming back to the Bragg-Brentano geometry that we talked about at the very end of last lecture. And remember, we said that, okay, the X-rays come in at low 2 theta angles. They're going to have a wide footprint on the sample, but not penetrate very deeply. And as we go to higher and higher 2 theta angles, as theta approaches 90, the penetration depth is going to get deeper. Now, we don't want in that experiment to have the X-rays go all the way to the bottom of the sample. That's bad for a few reasons. But we can use this idea of absorption that we talked about in this lecture to estimate what would be the penetration depth of the X-rays. So this formula, which is really assuming how far will the X-rays penetrate until there's only 1/10 of 1% of them left, is based on your linear absorption coefficient, mu. The bigger that is, the smaller the penetration depth. And then on sine theta, and that's just a trig thing. Well, when you're coming at a shallow angle, you can see that you go through quite a bit of the sample to penetrate down a little ways. And so that's why the sine theta term. When theta is small, of course, this makes the penetration depth small. As theta goes upward, approaching 90, then the penetration depth gets deeper. So this might be something that normally for many samples we don't have to worry about this in flat plate mode, but depending on your wavelength and the density or elements in your sample, it might be something just to check.